carbon is significantly more complicated than hydrogen because carbon has two types of orbitals. Like hydrogen, carbon has an s orbital, but in addition to that s orbital, it has three p orbitals. A p orbital looks like this. And the p orbital has two lobes. And the two lobes are in opposite phases of each other. And you have three of them. This is the pz orbital. One of them's located in each direction. Px orbital looks like this. And then you also have a py orbital, which I'll show pointing right at you. And then the other lobe is going back into your computer screen. And this is what carbon uses to form bonds. Now, carbon can form two types of bonds. It can form sigma bonds, like hydrogen, and these are direct bonds. Hydrogen, the two of them are right next to each other. It can also form pi bonds. Pi bonds use p orbitals only. These pi bonds have a tendency to be a bit weaker than sigma bonds. Where sigma bonds are directly at each other, pi bonds are between two p orbitals and they're more tangential. Well, you have dark with dark, light with light. You have an overlap here, but it's a much weaker overlap than the sigma, which is directly at each other. Okay, now, to further complicate things, carbon doesn't use the s orbital as is. Instead, it uses a hybrid orbital, which is a mixture of an s and either 1, 2, or 3 of the p orbitals, depending on what it needs. Single bonds, carbon-carbon single bonds, are sigma bonds. With a carbon-carbon double bond, they consist of a sigma bond plus one pi bond. A triple bond consists of a sigma bond plus two pi bonds. Now, thing to remember, sigma bonds have to use orbitals with s in it. So they have to use what are called the hybrid orbitals. Pi bonds use p orbitals only. You have actually three choices for hybridization. Your atom can be sp3 hybridized, which means you have 4 sp3 orbitals. All of them hybrid orbitals. This has a tendency to be a tetrahedral geometry. Bond angles roughly 109.5 degrees. no p orbitals are left. You also have sp2 hybridized, which you have two sp2 orbitals. Because you form a hybrid orbital, actually three sp2 orbitals, you form a hybrid orbital between an s and two of the p's, and you generate three sp2 orbitals, and you leave one p orbital untouched. This has a tendency to be trigonal planar. Bond angle, typically 120 degrees. So, sp hybridization uses a hybrid orbital between an s and one of the p's. So you end up with two sp orbitals and two p orbitals. So these molecules have a tendency to be linear. Bond angle, 180 degrees. Now, what is a hybrid orbital? It's easiest to describe the sp orbital, hybrid orbital. Basically, if you take the s and you overlay it with a p, and say you choose the light s, what happens is the light side reinforces this light side, but diminishes the dark side. And so you end up with an orbital much like a p orbital, except one of the lobes is enlarged and the other one is diminished. And so this is an sp orbital. Now, they could have come together in this phase, or what could have happened is they could have come together where one of them is in the opposite phase. So if we chose the opposite phase of the p orbital and overlaid that with the s orbital, what we would see is this light side gets bigger and the dark side gets diminished. That. Okay? So what we've done is we've used an s and a pz orbital to generate this sp. We could also use the s and the pz orbital to generate this sp. So we generated these two sp orbitals by using just the s and the pz. This leaves the px and the py orbital here. So these two sp orbitals look like this. And these are what forms a sigma bond. Hybrid orbitals form the sigma bond. These form the pi bonds. So a typical sp hybridized carbon is in an alkyne. Say, acetylene, where this carbon is sp, this carbon is sp, and so what it does is this carbon uses its sp orbital, one of its sp orbital, to form the sigma bond with this carbon. It uses the other sp orbital to form the sigma bond with this hydrogen, and then this carbon has two p orbitals left over, and that's what's used to form two pi bonds to the other carbon.